So today, our goal is to understand and apply the intermediate value theorem. The intermediate value theorem for continuous functions is defined as follows. A function, y equals f of x, that is continuous on the closed interval a to b takes on every value between f of a and f of b. In other words, if y naught is between f of a and f of b, then y naught must equal f of c for some c in the closed interval a to b. Now that's really mathy. Let's try and make it a little bit easier for us to understand in terms of an example. So here's an example of when the intermediate value theorem works and when it doesn't. So if we have a closed interval a to b, that means that we're looking at every single x value from a to b. So if we look at the x values from a to b in our example, what happens is every single value of y between f of a and f of b must get hit by the function somewhere. So if we're looking at this and I trace it out, if I look at every value of y between f of a and f of b, it gets hit by the function. So if I look at the function, every single value between those two red dotted lines gets hit. That doesn't mean that there aren't values that get hit that aren't between f of a and f of b. So it's very possible that within a function, for example, in this function, we have other values between a and b on the x-axis that hit y values that are not between our two dotted lines. For example, all of these values are not between f of a and f of b. They still get hit. If we have an example like a linear function, so I'm just going to draw a linear function real quick. If we have a linear function that starts here and ends here, there are no values outside of our dotted lines that get hit. I can have plenty of other functions. I can have a polynomial function, nothing outside the dotted lines gets hit. But there are some times when there are values where it gets hit outside of our dotted lines. So what the intermediate value theorem does not say is that all values must be between f of a and f of b. What it does say is if we have a continuous function, then if we know what f of a and f of b are, there must be some value of the function that hits everything along the way between f of a and f of b. So for example, if I said c was equal to this y value, there must be at least one point on the function where that y value is hit. Now, when we look at the counterexample, that's not continuous. So if I know where f of a and f of b are, or if I know where a and b are, there are some values between a and b such that f of a and f of b are like, it doesn't hit everything. So clearly, there's a huge gap in the y values there. So this does not hold unless it's continuous. So if we go back to our definition, a function y equals f of x that is continuous on a closed interval a to b takes on every value between a and b. So if I, for example, let's say I have y equals x squared, and I'm looking at the interval from 1 to 3. So if x is in 1 to 3, then what I know is y is the y values where this works, so 1, 1, 3, 9. If I kind of look at that graph from 1 to 3, all the values between 1 and 9 have to be hit on that function. So if I look at some value, let's say the value is 5. That's between 1 and 9. So in that case, there must be some value c such that f of c equals 5. And we can solve for it pretty easily. So f of c is equal to c squared. And we know that f of c must equal 5 at some point. So c equals plus or minus the square root of 5. Well, negative square root of 5 isn't in the interval that we're talking about, but positive square root of 5 is. So that means at positive square root of 5, which would be somewhere around here on the x values, we hit the y value 5. Okay, now let's go into your examples on your worksheet. Use the intermediate value theorem to verify that there is a 0 on the stated interval. So in order to verify that there's a 0, what that means is that between 0 and 2 for the x's, so x is between 0 and 2, one of them must be positive and one of them must be negative, and the function must be continuous. First, let's look at the function. It is a polynomial function. All polynomial functions are continuous. Okay, check. So now let's move on to actually verifying that this works. So if we take a look at f of 0, that's negative 2. We substitute in 2 to the function, we get f of 2 equals 14. So because between 0 and 2, our function values have to, since it's continuous, hit every single y value between negative 2 and 14, there is some value where f of c, some value c, must equal 0. And you could solve for it if you knew how to solve quintics. But since most of you don't know the quintic function, and actually I don't even know the quintic function because it's really, really, really hard, you would probably have to use your calculator in order to figure out what that value of c is. But it's not asking us for the value of c, it's just asking us to verify there's a 0. Now let's look at the second question. That's also a continuous function on the interval 2 to 4. So if we take a look at substituting 2 and 4 in, we find out that the value is 1 for both of them. Okay, so what does that mean? That means that between 2 and 4, there has to be some value that hits 1, and it can include 2 and 4. So we already know two values where it hits 1, when x equals 2 and x equals 4. So this doesn't actually tell us anything. In this case, the intermediate value theorem gives us no information. We cannot actually tell if there's a 0 due to the intermediate value theorem. Is there a 0? Well, we can check by solving the function. So we can clearly get x equals 3 to be a 0. So when x equals 3, there's a 0. But the intermediate value theorem doesn't actually tell you that, because if we look at the interval from 2 to 4, all the intermediate value theorem says is every value between 1 and 1 must be hit. And that's really not very many values. Again, like we talked about in the examples, it's possible that even though the intermediate value theorem holds, there are values outside of that range that get hit. But that's not actually telling us anything by the intermediate value theorem. Okay, next couple questions on your notes. Use the intermediate value theorem to find an interval of length 1 for which there is a solution to x cubed minus x plus 1 equals 0. Well, this is kind of the answer, but let's figure out why that is. So if we look at the graph of x cubed minus x plus 1, if we look at the graph of x cubed minus x plus 1, we want that to equal 0 somewhere. Okay, so if we look at the graph, we are looking at it and we say, oh, there's a 0 here. That's between -2 and -1. So because it's between -2 and -1, what we can do is we can substitute in -1 to the function. If I substitute -1 into the function, I get 1. If I substitute -2 into the function, that's actually off our screen, but I would get -5. Because that's the case, every single value on the interval -2 to -1, or on the interval -2 to -1, sorry, I misspoke. So let's try that again. On the interval of x between -2 and -1, every y value between -5 and 1 must have some value that works. So there is some f of c, there's some c, such that f of c equals 0 between -2 and -1. We could solve for it if we knew the cubic equation, but since we don't know that, you would probably have to use a calculator and in order to actually figure it out. Finally, let's do a few true-false statements. What I want you to do is take a few minutes, pause the video, and then we will come back and go through these together, but I kind of want you to try these on your own. So I'm going to pause for 5 seconds. You try these by pausing it, and then I'll come back and go over all the answers. Okay, if g of x is a function with g of 0 equals 4 and g of 3 equals 7, then there's some x between 0 and 3 such that g of x equals 5. So if we look at the function, g of 0 is 4, g of 3 is 7. That means that some value between 0 and 3, there has to be a value g of x where there has to be some g of c where that equals 5, right? Actually not correct. What is missing from this piece of information, or what's missing from this sentence, is something telling you that g of x is continuous. Since it doesn't say that it is continuous, we can't assume that it's continuous, and therefore we must call this false. Is there a value between 0 and 3 such that g of x equals 5? There could be, but we do not have enough information in order to actually tell. Statement 2, let f of x be this function. Well, since this is a polynomial function, it is continuous. Is there a point between 1 and 2 where f of x equals 4? Well, f of 1 is equal to -3, and f of 2 is equal to 8 plus 8 minus 5, so that's 11. That means that since this is continuous, on the closed interval for x, 1 to 2, there must be every single y value hit between -3 and 11. So the intermediate value theorem says that this statement must be true. Statement 3, if f of t is continuous on the closed interval -5 to 3, okay, it tells us it's continuous, so that's good. If f of 5 equals, or f of -5 equals 6 and f of 3 equals -9, then f of 0 could be equal to 10. That is true, but not due to the intermediate value theorem. So again, if we have a picture where f of -5 is 6 and f of 3 is -9, so that's somewhere down there, it doesn't have to be true, but all the question is asking for is saying that f of 0 could be equal to 10. So is it possible that our graph looks like this and f of 0 is not 10? Very possibly. Everything between -9 and 6 for the y values must be hit. But that doesn't mean that everything has to be hit. So we could have a graph that looks like this, and this could be 10. Finally, a function f of t depicts the quantity of flim-flam present at time t. At t equals 0, there were 10 cubic cans of flim-flam, and a week later there were 40 cubic cans of flim-flam. At no time were there exactly 20 cubic cans of flim-flam present. Therefore, the function f of t is not continuous. That's true by the definition of the intermediate value theorem, because if there's stuff between 10 and 40 from time t equals 0 to time t equals 7 days, or whatever they're doing in terms of t, then there must be something that has 20 cubic hands if there is a continuous function. And that's our lesson on the intermediate value theorem.